Welcome to another exercise for the workbook Statistics. This time I'm going to focus on measures of contingency, or rather measures of association for nominally scaled variables. So let's have a look at the exercise. Here I have a group of men and women is surveyed in regard to which series they know. It's about shears and friends. Results are summarized in the table below. And our task for this table is use a suitable normalized statistic to quantify the strength of the relation between viewers' gender and the series they know. Well, we could use the Yule coefficient here, but I would rather go for a more sophisticated version, and they're all based on chi-squared. So let's start by getting chi-squared and the respective, frequencies we need for the calculation of chi-squared. The first step is the calculation of marginal frequencies. So we're going to copy the table here, and then we're going to add row sums and column sums. So I'm going to add up all the entries in each of the two columns. I'm going to do the same thing for each of the two rows. Finally, going to add up all of these values, so the 70 plus 80 or the 33 and the 117, giving me a total of 150 observations. Based on these marginal frequencies, I can then calculate the expected frequencies, those values which I expect to result if the data were to be evenly distributed, following only those marginal frequencies. For this, I'm going to copy the table, usually without this stuff here in between, with just the marginal frequencies from before. Those values here, the expected frequencies, I can calculate following this formula. This formula might look a bit strange at first glance, but it's actually pretty easy to understand. It's just for this entry, I'm going to look up the value in the column and in the row for the sum, those two. I'm going to multiply those two. And I'm going to divide this by the overall number of observations. And that's what I'm going to do for all of them. Here I have 70, 117, so those two multiplied, divided by the 150. I'm doing the same thing for those two. This gives me my expected frequencies. And if I want to know whether I did this correctly, I can simply add up those two expected frequencies, because they will again give me the 70. I can add up those two expected frequencies, and they will again give me the 33. So that's actually something which I can check whether I did this step correctly. Well, that's my main first part. So I'm going to copy the original values and these expected frequencies into one new table on the next slide. This table looks like this. Then we can use these values to actually calculate the chi-squared statistic, which is just this formula. Again, this looks relatively complicated, but it's nothing else than we're going to calculate for each of these four different fields this expression. This is just expected frequency, 15.4, minus actual frequency, 21, to the power of 2, divided by the expected frequency, 15.4. We're going to do this for each of the four different fields here. And we're going to add up the results. So I'm going to write this down here, step by step by step. If you want to have a little bit more of order, you could also do this in this table. So you can put each in this part where it actually belongs. Helps you to actually keep track whether you considered all of the relevant parts for the calculation. In the end, just add up all of these values, or partial values, which we get here, giving us then as a final result 4.8952. Well, that's chi-squared. Chi-squared itself doesn't really tell us a lot, because it's somewhere between 0 and infinity. So we only know if it's very small, but 4.89 or 4.9 doesn't really tell us a lot. So don't know, it's a strong, weak, whatever. So we need to adjust this. We need to normalize this to a statistic which lies somewhere in the interval between 0 and 1, ideally. Here we have different alternatives. I'm going to go with the contingency coefficient, or the corrected contingency coefficient. For this, I'm going to use my chi-squared as calculated before, and I'm going to insert this into the formula. So it's chi-squared divided by chi-squared plus the number of observations, and then the square root thereof. Here I had 150 observations, so I'm going to calculate it and get 0.1778. That's already a result which will also be smaller than 1. However, this has the big disadvantage, it's not possible, or usually not possible, to get 1 here. So it's not really bounded by 0 and 1, so we have to correct this. The advantage of calculating the contingency coefficient, however, even in this form, is that we considered the number of observations. So if I have more observations, I have more potential for deviations, and that's what we took care of with this coefficient. So in the next step, we're going to consider another problem factor, and that's the size of our contingency tables. Because if we have a larger contingency table, we have more room for deviations as well, because we have more parts added up for chi-squared. So for the correction of the contingency coefficient, we need this help value m, this parameter m, which is just the minimum of the number of columns or rows. Well, here I have 2 columns, 2 rows, so the minimum of column and row number is just 2. Then I get this correction factor based on this m, which is just the square root of m divided by m minus 1. M is 2, so 2 divided by 1. So I have correction factor of square root of 2 here. So I'm multiplying my contingency coefficient with square root of 2, giving me an end result of 0.2514. This is something which I can interpret using the same thresholds as I know from other measures of association. So this is larger than 0.1, smaller than 0.3, meaning this is actually a weak relation. I cannot say anything about the direction because, well, it's nominally scaled. We do not have any kind of orientation here, but, well, it's a weak relation we have here. And that's about it on this exercise. So I hope you enjoyed it. I say goodbye and see you next time.